Let us continue our discussion on advanced encryption standard. In the last class, we were looking at finite field arithmetic. We looked at how to perform addition, division, multiplication on a Galois field. In today's class, we'll be looking at how AES works. What are the various steps involved in advanced encryption standard? So advanced encryption standard was established in the year 2001 by the US National Institute of Standards and Technology, and this strategy has been adopted by the US government and it is now used worldwide in various products. This strategy supersedes the data encryption standard, which we have learned in our previous lectures. We have seen the disadvantages of this. And advanced encryption standard is a symmetric key algorithm, which means that we are going to use the same key for both encryption and decryption. AES is a block cipher, which means that we are going to take the input message, break it down into blocks of 128 bits, take each block and convert it into ciphertext. So I was just scanning through the internet to see where all advanced encryption standard is being used, in what kind of products it is used. So I've taken some samples for our understanding. So we all know SanDisk and the popular USB drives that we use. And in their product page, they have clearly mentioned that SanDisk Secure Access Encryption Program is a 128-bit AES encryption. Likewise, Western Digital, in their product page, they have mentioned that they are using a built-in 256-bit key AES hardware encryption strategy. And even in the product page of apple.com, I have found that they are using a dedicated AES engine to support line speed encryption. Not only that, AES is part of a lot of products, even your browsers. So AES is being used extensively worldwide. We look at further details regarding AES. The advanced encryption standard encrypts messages in blocks of 128 bits. I told you, right? The message will be coming in and we have to split that in blocks of 128 bits. So we're going to take 128 bits at a time, convert that into a ciphertext block. And for encryption and decryption, we need a key. Here, three kinds of keys are allowed. That is, we can take a key of 128 bits in length, or we can go in for a key of 192 bits in length or 256 bits in length. The only thing is, when you go in for a larger key size, the encryption takes more time when compared to a 128-bit key size. Again, the number of rounds in encryption is dependent on the key size. If you take 128 bits as your key size, then we need 10 rounds in our encryption strategy. If you take a key size of 192 bits, then we need 12 rounds in our encryption strategy. If we take 256 bits, then we have to go and have 14 rounds in our encryption strategy. So we'll be looking at what a round is in the coming slides, but the number of rounds increases with the increase in key size. So let us now take a look at the overall block diagram of an advanced encryption standard. The very first thing is message is broken down into blocks. So each block is of 128 bits. As you see here, this is a plain text message which is coming in. It is broken down into blocks of 128 bits. This is a 128-bit block. This is a 128-bit block. So we take one block at a time and then we encrypt it. And the next thing that we need is a key for encryption and decryption. So the key size that we are going to take for our understanding is 128 bits. So we're going to get in a key of 128 bits, and using this key we are going to generate 10 more different keys. So we'll start from subkey 0, subkey 1, we'll go up till subkey 10. So just using 128 bits of this key, we're going to go and generate subkey 1 to subkey 10. These are 10 different subkeys, each of 128 bits in length. So every subkey is 128 bits. And what is this subkey 0? It is nothing but this key. So we are going to get this key and use it as subkey 0. So it is 128 bits. So we're going to select a key of 128 bits that becomes subkey 0, and using this 128 bit key we are going to go and generate 10 different subkeys. So what is the use of all these keys? We are going to use them in our algorithm. Say first we are going to take the input key that we have selected, so that is this key. So subkey 0 is nothing but the key that we have selected, the original key, and we are going to perform an XOR operation, XOR with our input text block. So this step is called adding round key. You are just adding round key here. After the XOR operation, this output, which is 128 bits, is being fed to round 1, and round 1 also makes use of subkey 1, which is 128 bits, and we'll be performing some steps in the round 1, and then that output of 128 bits will be going to round 2. Round 2 will be making use of subkey 2. Likewise, that will go to round 3, and round 3 will be using subkey 3, and finally it will be ending up in round 10. As I told you in the very first slide, if you take a key size of 128 bits, the number of rounds that we have to use is 10 rounds. So round 10 will be making use of subkey 10, and finally the output of round 10 will be our ciphertext block. So this ciphertext is corresponding to the 128-bit message block that we have taken. So what are the things that we have to understand from this block diagram is, we have a message block that's coming in, and we have a key that we need to select. Once after selecting the key, we need to expand this key. We call that key expansion in Advanced Encryption Standard. Let me write it here. What is this? This is key expansion. Why I say this is key expansion? Because we are taking 128-bit key and expanding it to 10 different keys, each of 128 bits. So that is one phase that we have to learn. The next phase that we have to learn is, we take this message block, we XOR that with the key that we have taken. That is the next step. After that we get into the rounds. So we feed this output to round 1, round 2, round 3, and each round makes use of a subkey, and all the subkeys are of 128 bits in length, and the output from the final round will be your ciphertext block. So as part of AES encryption, we are going to understand what is key expansion algorithm in Advanced Encryption Standard and what's happening in each of these rounds. So all these rounds are identical. If you understand one round, the other rounds are similar. Now let us understand the strategy behind key expansion in Advanced Encryption Standard. For that, first we need to take a key. So I have taken this key. The key is Satish CJ is boring, a very interesting key. And this key is actually 128 bits. What I mean by saying that this key can be represented in 128 bits, it's represented like this. So this is what is the meaning of Satish CJ is boring. And I'm converting this key into hexadecimal characters. So I'll take 4 bits and then I'll write the corresponding hexadecimal value for that. So what is 0111? It is 7. And what is 0011? These 4 bits represent a 3. So 73 is the hexadecimal representation of the first 8 bits. Or we can say the first 8 bits to be a byte, right? The first byte in our key can be represented in hex as 73. And these 4 bits 0110 correspond to 6 in hexadecimal, and 0001 corresponds to 1 in hexadecimal. So the next byte can be represented as 61 in hexadecimal. Likewise, we can go and represent our key in hexadecimal. So each one here is a byte. So this is a byte, this is a byte. Why I say it's a byte? Because it takes 8 bits. So this is a byte, this is a byte. So we have totally 16 bytes here. Each byte is nothing but 8 bits. So we have taken this key and we have a byte level representation of the key. And for better understanding, I have even mapped that. So S is equivalent to 73. A is mapped as 61. T is mapped as 74. I is mapped as 69. Everything here is a byte. 74 is a byte, 69 is a byte, 73 is a byte, 68 is a byte. Like that we have 16 byte representation of the key. So now what we'll do is we can go and just for better understanding, say this is byte 1, 73 is byte 1, 61 is byte 2, B2, 74 is byte 3, 69 is byte 4, and so on. So 67 is byte 16. Now what we have to do is we have to convert this key into a 4x4 matrix. So how many elements will be there in a 4x4? 16 elements. So how we convert this is the representation of the key as a matrix. So we represent B1, B2, B3, B4, B5, B6, B7, B8, and we complete the matrix. So we are going to just convert this key like this. So when you convert it like this is how your key representation will be in the form of a 4x4 matrix. So this is byte 1, byte 2, byte 3, byte 4, byte 5, byte 6, and so on up to byte 16. Is that clear? So now we have taken a key and we have somehow converted that to this format, and in this format you consider the first column. This column is called a word, and this column is another word. So this is another word, this is another word, this column is another word, this column is another word. So we can say this is word 0, this is word 1, this is word 2, this is word 3. And what is the size of each value here? That is 1 byte. Right? This is a byte, this is a byte, this is a byte, this is a byte. So how many bytes we have here? For a word we have how many bytes? We have 4 bytes. So it means a word is made of 32 bits. Very simple. This is a word and everything is a byte. So 4 bytes, and how many bits? 32 bits. So how many words you have in a key? You have 4 words, and I have given the representation as word 0 to word 3. So now we have to use these 4 words and we have to expand it into words starting from W0 to W43. So this is key expansion. That is, you take these 4 words and you expand that till W43. And we already have W0, W1, W2 and W3. It is nothing but whatever that is given here. So this is W0, this is W1, this is W2, and this is W3. The first 4 words is already known to us, that is from the key that we have taken. And using these 4 words, or using this key that we have taken, we have to determine the remaining words, that is words starting from 4 to 43. We have to determine the remaining 40 words. Using these 4 words, we have to go and expand and get the remaining 40 words. So what is the use of these 40 words? We'll be taking 4 words at a time and then we'll be using it in a round. Say for instance, these 4 words, we call it to be subkey 0. Right? This is subkey 0. Using subkey 0, we will generate W4, W5, W6 and W7. This is subkey 1. So this will be used in round 1. Likewise, using these 4 words, we will go and generate the next 4 words. That is W8, W9, W10 and W11. That will be subkey 3. And using this, we will be generating the next 4 words. So every 4 word will be used for generating the next 4 words, and a 4 word combination will be used as a subkey. What is a word? How many bits it has? 32 bits. So 4 words in the sense it's 128 bits. I hope you have understood. Now let us take a look at how to expand the available 4 words into 40 words. That's what we are going to see. So this is the key that we have taken, converted into bytes, and we have represented that as a 4x4 matrix. And from here we have to go and generate all the 43 words. What is known to us is this is W0, this is W1, this is W2, this is W3. So the first 4 words is available to us from the key that we have taken. And using these 4 words, we will generate these 4 words. So this will be used in round 1. And again, using these 4 words, we'll go and generate the next 4 words that will be used in round 2. Like that, we have to generate 40 words used in 10 rounds, 4 words per round. Okay. So now let us go and take a look at this strategy, how to use these 4 words and generate the next 4 words. If we understand this, everything else, the generation of other words will be exactly similar. So what we are going to see now is we have 4 words here, that is from the original key. Using these 4 words, how to generate the next 4 words, W4, W5, W6 and W7. This will be used as a sub key in round 1. So for that, what we have to do is we have to take W3, pass it to a function G. So G uses W3, does something to it, and we have to take W0, and the output of G will be XORed with W0, word 0, and that will become word 4. So you take word 0, you take word 3, pass it to G, the output is XORed with word 0, you get W4. So once when you get W4, things are a little easy. You take W4, you XOR that with W1, that will become W5. So once when you get W5, you take W5, you XOR that with W2. So W5 XORed with W2 will give us word 6. So once we have word 6, we can take word 6, XOR it with W3, and then that will lead to W7. So using these 4 words and this function and all XOR operations, we were able to expand it and get the next 4 words that will be used for round 1. Now using these 4 words, again using the same strategy, we'll be generating what? W8, W9, W10 and W11. So we'll take W7, we'll give it to G, and this output will be XORed with W4, and you will get what? W8. So again W8 should be XORed with W5 to get W9, and W9 should be XORed with W6 to get W10, and W10 should be XORed with W7 to get W11. So using these 4 words, we'll be able to generate the next 4 words that will be used in round 2. Like that, we will be generating all the 40 words required for 10 rounds. But then the question here is, what is this function G? What does G mean? So what is the input that G takes here? G takes W3. So we can also represent W4 like this, right? W4 is equal to W0, that is XORed with the output of the function G. That's what is given here. W4 is equal to W0, word 0, XORed with the output of the function G, which takes W3 as the input. So now let us take a look at what is this function G, why we need that. So what is the input to G? G takes W3. So what is W3 from our previous slide? This is word 3. So what is word 3? Word 3 is this one. This entire thing is word 3. So we are going to feed this as an input to this function G. Let's see what it does. So this is word 3. Now what we are going to do is, the very first step is we are going to take W3 and do a cyclic left shift by 1. So what is W3? It is nothing but 72, 69, 6E, 67. So we are just going to move 72 at the end and move every other byte one step to the left. So what will be the output here? It's 69, 6C, 67, 72. So that is the very first step. Perform a cyclic left shift by 1 byte and you will be able to get the RotWord. So this is nothing but the output after you perform a cyclic left shift by 1 byte on W3. So that's what is given here. RotWord performs a 1 byte circular left shift on a word. So this means that if you have B0, B1, B2, B3, your output will be nothing but B1, B2, B3, B0 pushed to the end. I hope you have understood what is RotWord. The next step is we need to take this RotWord and then we need to find a subword. So how will you find a subword from the RotWord? So subword performs a byte substitution on each byte of its input word using the S box. So you have to see what is this X box. So it's very simple. You're going to take every byte, substitute that with another byte. For that we'll be using this box called an AES S box. Let me erase this ink here. We're going to take 69. Here 6 is used for identifying the row. So where is 6? This is corresponding to 6. And 9 is used for identifying the column. So where is 9? 9 is here. We'll see where these two things intersect. So you have this one. So we are going to substitute 69 as F9. Likewise, can we do it for 6E? 6 is here. Where is E? E is here. Right, so this is where E and 6 intersects, so the value is 9F. Likewise 67, you have 6 and where is 7? 7 is here, so the value is 85. Likewise 72, 7 is here, so this is 0, 1 and 2, the value is 40. The next step is nothing but byte substitution. For this we are going to use this S box. Take every byte in the RotWord, substitute that with another byte using the S box. So this is what we have achieved. So once when you have achieved the subword, the next step is we have to perform an XOR of the subword with a constant called the round constant. So what is this round constant? Say what we are trying to generate here. Do you remember? Say we are having W0, W1, W2 and W3. So these four words we are going to generate the key, that is W4, W5, W6 and W7. So this is the subkey one that will be used in round 1. So this round constant will be used according to the subkeys you are generating for that particular round. Now we are going to perform an XOR of the subword with round constant 1. In round constant 1, the first byte alone exists, the remaining 3 bytes will be zeros. You take any round constant, the first byte as the value, the remaining 3 bytes are nothing but zeros. So what is this round constant? How will I select that? Say now I am trying to find the value of W4, W5, W6 and W7, which is corresponding to round 1. So I will take the round constant round R1. What is this R1? It is nothing but a word of 32 bits. So I will take this, perform an XOR of round constant with Y1. Is that clear? If I am going to find W8, W9, W10, W11, this is actually for round 2. So which round constant I will be using? I will be using R2 when I am trying to find W8. Okay. So what we are going to do here is we are going to take this subword. We have selected the round constant R1. So this is the binary representation of the subword and the round constant. We have to perform an XOR. So this XOR gives us the output of G of W3. So all these things we are performing to understand what is the output of the function G. So we have completed G. What are the steps in G? Take W3 and then you find the RotWord by doing a circular left shift of 1 byte. And using the RotWord, you find the SubWord, which is a byte substitution. You take every byte and substitute that with another byte using the AES box. Once when you get the SubWord, what next you have to do? Take this SubWord and use the round constant table. Select the corresponding round constant. Say here we have selected R1 because we are finding the sub key 1 for our round 1. And you perform an XOR. So this result, what we are seeing here, is nothing but the result of the function G. And I have represented that result in hexadecimal. Say first 4 ones represent an F, the next thing 1, 4, 3 zeros represent an 8. So the output is represented in hexadecimal. I hope you have understood what function G does. So what is that we are trying to perform? We have word 1, word 2, word 3, and we are trying to perform and identify the next 4 words W4, W5, W6 and W7. So for this, what we did initially, we took W3 and we have fed that to the function. We have found the result of this from the previous slide. What next thing we have to do? We have to take W0, we have to XOR that with this output. So this output we have determined that it's in our previous slide. Now we have to perform an XOR with W0. What is W0? This is W0. So that's what I have shown here. W0 XORed with GW3. This will give us the result. So what is that? W0 XORed with G of W3. So this result is nothing but W4. So finally we have achieved what is W4. It is nothing but 8B FE F129. So once when you get W4, things are quite easy. What you have to do, you have to take W4 and then you have to XOR that with W1. So we know what is W4, we know what is W1. I have given here, this is W1, this is W4. Take the binary representation of the X values. Now when I perform an XOR, so the result I have, so that is nothing but F8969243. The result is nothing but W5. So we have achieved this. Likewise, now you take W5, which is here, you perform an XOR with W2, you will be getting the result like this. Likewise, you take W6, you perform an XOR with W3. So when you perform an XOR, you're going to get this result. The tougher thing here is determining the very first word. For this, we have to use this function G, and we have to compute what is G of W3, and then we have to XOR that output with W0 to get W4. Once when you get W4, the remaining things are simple, just XOR, XOR, XOR with W1, W2 and W3, you're going to get the output. So finally, using these 4 words, we have generated the next 4 words, and these 4 words will be used as a sub key in round 1. We can call this sub key 1. So sub key 1 is nothing but starting from W4 to W7. If you want to find sub key 2, what you have to do? Take W7, give it to G. So G takes W7. And now after you get the output of that G, you have to perform an XOR. So the same strategy repeats. So this will be W8. So once when you know W8, you XOR W8 with W5 to get W9. So you keep XORing the output with the next word so that you get the next word. So like that you go on achieving what? You start from W0, you go on achieving up till W43. Let me erase all the ink on the slide. So we have started with W0, W1, W2, W3, the original key. We were able to find W4, W5, W6, W7. Like that, the same process continues until we reach word 43. And in every round, 4 words are used as an input. So these 4 words are used as an input to round 1. And the next 4 words will be used as an input to round 2, like that. And it continues. So we have understood this part in our block diagram, that is what is key expansion and how you achieve key expansion in advanced encryption standard. We have looked at the strategy behind that. So I've just mentioned the keys as words. So this key that we have taken has got word 0, word 1, word 2, word 3, that is subkey 0. From this we generate another subkey, word 4, word 5, word 6, word 7. From this we generate the next subkey, word 8, word 9, word 10, word 11. So 4 words will be used as a subkey for every round. This is again nothing but 128 bits. Each word is 32 bits. 32 into 4 is 128 bits. So are you all clear with how we perform key expansion in advanced encryption standard? Okay. So this part is done. Now let us understand this part. That is taking a message block of 128 bits and adding the round key. What is adding the round key? Taking the subkey starting from word 0 to word 3 and then performing an XOR with the input text block. We'll see this part now. What is this? Okay. That is called the add round key step, the very first step that I've showed you, the very first step. So we'll take a message. The message is secret message now. This corresponds to 128 bits. Say in advanced encryption standard, we are taking blocks of 128 bits and encrypting it. So I've taken a block of plain text that can be represented exactly in 128 bits. And those 128 bits are represented as bytes here. So each takes 4 bits. So this is 4, this is 4. This is actually a byte, and 7 and 3 are hexadecimal characters. The same way that we did for the key. So we represent this message in hexa, and 73, how it is represented? 7 is represented in 4 bits and 3 is represented in 4 bits. So this entire thing is a byte. So again, this message is now converted to some kind of byte representation. So we have the message now in 16 bytes. Now you would have judged what we are going to do next. We are going to convert that to a state array or the 4 by 4 matrix. So this is a byte, this is a byte, this is a byte, right? We are arranging that into a state array. They say this is a state array, a 4 cross 4 matrix. And each element in the matrix is a byte. So in advanced encryption standard, we are working with bytes. Please keep that in mind. So how we arrange this bytes? This is byte 1, byte 2, byte 3, byte 4. Byte 1, byte 2, byte 3, byte 4. Next comes byte 5, byte 6, byte 7, byte 8, and so on until we reach byte 16. The very important thing is you take the message, make a byte representation of the message, and convert that 128-bit message into a 4 cross 4 matrix, wherein each element in the matrix is a byte. So now our input message is ready. This should be XORed. We have to perform an XOR operation with the key. We have already selected the key. Satish CJ is boring, and this is the byte representation of the key, and these are the words in the key. What are the words? It starts from word 0, word 1, word 2, word 3. Now you perform an XOR. What is an XOR? You take 73, you perform an XOR with 73. So how you perform an XOR? You take 73, have the binary representation of 73. Likewise, you have 73, you have the binary representation. What is an XOR? Only when one of the bits is a 1, your output will be a 1. So here 0 0 0 1 1 0, so 1 1 0 1 1 0. So the result will be all zeros. So the output matrix you're going to get 0 0 as the value. Like that, you take 65 and 73, you perform an XOR, the value will be 1 6. So you have a 73 here and a 73 here. If you perform an XOR, the value is 0 0. So this is the first step, that is called add round key. Take the message, convert that to a 4 matrix. Take the key, convert that to a 4 matrix having all bytes. Perform an XOR, you get the output. This is called a state array. So now we are here. We have finished key expansion. We have finished converting our message to a state array, and we have performed this XOR operation, and the output is a state array. So now this output, the state array, will be going to round 1, and round 1 will also be utilizing our key starting from W4 to W7, the 4 words. The next question comes to our mind, what is happening in this round? If you understand what is happening in one round, the same thing applies to all the other rounds, except for a slight variation in round 10. So the next question we have here is, need to understand a round. What are the steps in a round?